Good morning. So I want to continue our discussion of synthetic organic chemistry. And in a way, chapters 6, 7, and 8 sort of go together. In chapter 6, we learned about functional group transformations, focusing mainly on not building up the carbon-carbon backbone of molecules, but understanding how different functional groups related within the molecule. Chapter 7, and to some extent chapter 8, they really go together, focus on building up molecules, on synthetic organic chemistry. Chapter 7 focuses on carbon-carbon bond-forming reactions, and it's, as presented in the textbook, it's a really cool chapter because it presents just a ton of synthetic organic chemistry, a lot of things you've seen before, but also new stereochemical concepts like new concepts like stereochemical control and maybe a little bit of organometallic chemistry. What I want to do is to, over the course of, well, collectively about 6 or 7 lectures, and for chapter 7 about 3 or 4 lectures, talk about carbon-carbon bond-forming reactions. And I've tried to group things roughly into groups that go together. What I want to do today is to talk about the importance of the carbonyl group, which really is a linchpin in synthetic organic chemistry, and talk about the role of the carbonyl group in synthetic organic chemistry. We're going to see a lot of reactions you've seen before, Aldol reactions, other enolate reactions, the Claisen condensation, not to be confused with the Claisen rearrangement, which is a 3,3 sigmatropic rearrangement, but the Claisen condensation. If we have time at the end, the Michael addition reaction. Probably in the next lecture after Friday's midterm exam, I'll move on to nitrogen analogs of carbon-carbon bond-forming reactions, nitrogen analogs of the carbonyl chemistry, and we'll talk probably about the Mannich reaction and maybe some enamine chemistry. All right, so to begin, for many, many carbon-carbon bond-forming reactions, we're talking about the reaction of some carbon nucleophile, which I will write as C-. Now, you don't get naked carbanions in carbon-carbon bond-forming chemistry. And in fact, if anything, the 3rd edition of your textbook has maybe a little bit too much of a propensity to take organometallic reagents like organolithium reagents and Grignard reagents and draw them as carbanions. The 2nd edition doesn't so much. I mean, it's a shorthand we think about, but you really have a covalent bond. So when I'm writing a carbon nucleophile like this, this is a shorthand for something that is like a carbanion, for example, an enolate. And in turn, reaction with a carbon electrophile, which I will shorthand as C+. Now, you do get carbocations in organic chemistry. You get sort of plain carbocations like a tert-butyl carbocation in a Friedel-Crafts alkylation. But for the most part, what I'm talking about, and you get sort of semi-carbocations like a protonated carbonyl group, which has a carbocation resonance structure, an oxocarbenium ion, as well as the 8-electron resonance structure. But what I'm talking about here really is a conceptual shorthand for a carbon with a delta positive on it reacting with a carbon with a delta negative on it to form a carbon-carbon bond. And this type of conceptual shorthand is very useful in thinking about reactions because it allows us to come up with buckets or ways of pigeonholing species in reactions where we can think about them. So for example, what we'll be talking about today are enolates, and I can, as a shorthand, write an enolate like this. I'll put the negative charge in quotes here. And we'll see, and you'll see me write them in just a moment. But what we're talking about in terms of reactants is enolates of aldehydes and ketones, or enolates of the carboxylic acid family, and again, this is where that grouping we were talking about before, that grouping of the carboxylic acid family together, of carboxylic acids and esters and amides and even nitriles, becomes useful because you're recognizing that all of those groups have, including the nitriles, have very similar properties. And now what I'm saying here is we can group them even with aldehydes and ketones under the rubric of species that are able to stabilize a negative charge at the alpha position. And in the chemistry we're going to talk about today, in aldol chemistry and Claisen condensation chemistry, we're talking about reaction of these types of species. This was just an X, by the way, over here. Again, a very generic group, whether I'm talking a carbon or an ester group or whatever. Anyway, we're talking about the reaction of these species with some type of carbonyl compound at the carbonyl carbon, which I can, as a conceptual shorthand, remind myself of that delta positive on the carbonyl carbon by writing a little plus. So this is just the bucket I keep things in my mind. And again, we're talking about aldehydes and ketones, but also enolates, also carboxylic acids, the carboxylic acid family. All right, so why don't I begin with some specific reactions under this broad conceptual rubric. One of my favorite reagents to make an enolate is LDA, because in practice, LDA is just, it does the job. It is a strong base that pulls off an alpha proton, generally very cleanly. Let me remind us of this. It is my workhorse compound. It is my go-to compound. Let me remind us of this with the idea of taking some ester. I'll take ethyl phenylacetate, the ethyl ester of phenylacetic acid. If I treat ethyl phenylacetate with LDA, usually in THF, usually at -78 degrees, often, by the way, you will generate LDA in situ by, at 0 degrees in an ice bath, adding N-butyllithium to diisopropylamine. N-butyllithium is a very strong base. Diisopropylamine is a strong, the anion LDA is a strong base, but not quite as strong. pKa of butane is 50, pK of diisopropylamine is about 36. Anyway, you can think of LDA as being sort of a workhorse base that you can generate in situ. Anyway, if I use my LDA, generate the enolate, add methyl iodide, this is just a great recipe for a carbon bond forming reaction, for an alkylation reaction. And as I said, this is going via the enolate. Now, when I write enolates, I generally like to write them like so, in the covalent form, in the major resonance form. But realize this is a conceptual shorthand for the ionic form. As I said, enolates are mostly covalent. They are polar covalent bonds. So this is a conceptual shorthand for this, which in turn is a conceptual shorthand for this. In other words, in the back of all of my mind, when I think about the generation of the enolate, is the enolate has this structure. I can think of it as a carbanion-like species. I can think of that polar covalent bond, and I can think of resonance structures. All right, so that shows us this carbanion-like behavior. Now let's talk about the carbocation-like behavior of carbonyl compounds. And by way of review, I want to write two reactions on the board. One is the reaction of benzaldehyde with a Grignard or organolithium reagent. So Grignard and organolithium reagents are sort of the go-to simple, old-fashioned, old organometallic reagents. And so I'll take methyl magnesium bromide, or I'll take methyl lithium. Methyl magnesium bromide you generate from methyl bromide and magnesium metal, usually in an ethereal solvent. Methyl lithium you generate from lithium metal and methyl bromide or methyl iodide, often in a hydrocarbon solvent. Both of these organometallic reagents, in practice, one can buy in conveniently septum bottles. They're reactive with water, they're reactive with air, but they're very easy to handle in the laboratory. So if in the first step I add methyl magnesium bromide or methyl lithium, and the second step I carry out an aqueous workup, I add a molecule, I add an equivalent of my methyl lithium or methyl magnesium bromide to the carbonyl compound to get the corresponding alcohol. In turn, I form a new carbon-carbon bond. The carbonyl acts as an electrophile. Its delta plus property is present in the reaction. The methyl magnesium bromide or methyl lithium acts as a carbon nucleophile. In the back of my mind, even though I'm not writing this, even though I'm thinking of this, say, as CH3MgBr, a covalent bond, even though I'm knowing that, I'm also thinking of this as an ionic resonance structure and saying, OK, I can think of it as a methyl anion. Now, as I said, many, many properties end up being similar, whether we're talking about the ketone or aldehyde family or whether we're talking about the carboxylic acid family. But there are some significant differences. So for example, if I take an ester, if I take, let's say, ethyl benzoate, and I carry out the same reaction, treating the ethyl benzoate with methyl magnesium bromide or methyl lithium, and then carrying out an aqueous workup, oops. I get addition of two equivalents. Now you might look and you might say, OK, but I didn't draw two equivalents over the arrow. I probably wouldn't. Or I might write excess, often abbreviated as XS. But the main point here is not only that two equivalents add, but that the nature of the beast is you really can't stop the addition at one equivalent. Addition of one equivalent is not generally feasible. If I use only one equivalent, if I mix 1 mole of methyl magnesium bromide and 1 mole of methyl benzoate or ethyl benzoate together, I will get mostly addition of two equivalents and no equivalents. In other words, mostly both this product, the alcohol, and unreacted starting material, and a little bit of the methyl ketone where one equivalent is added. The tetrahedral intermediate that forms after the first addition breaks down, kicks out ethoxide anion. the resulting ketone is even more reactive, more electrophilic than the corresponding ester, and so you get a second equivalent adding. There are various tricks within the carboxylic acid family to stop at one addition. Your textbook, for example, mentions that nitriles are an exception because you're not kicking any species out. You often can go ahead and add an alkylithium to a nitrile and get only one addition. Or acid chlorides are special with organocuprate reagents. So if I take benzoyl chloride and lithium methyl cuprate, then I can go ahead and add one equivalent. But the general rule of thumb for addition of Grignards and organolithiums is you can't control it. All right. With that said by review, and with this overarching framework of nucleophiles at the alpha position of carbonyl compounds and electrophiles at the carbonyl group, I want to give you another very useful conceptual framework that really runs in my understanding and my thinking about reactivity, and that is the role of pKa. Particularly the role of pKa in enolate formation and bases. And I keep a few numbers in my head, not many, but enough that I can grab onto them and use them in my thinking. So if we have some generic ketone or aldehyde, and I want to keep one pKa in my head, I would keep for the hydrogens alpha to the carbonyl about 20. Now the truth is there are slight variations. Aldehydes are a little bit more acidic. The pKa is a little lower for the alpha position. A phenyl group may make you slightly more acidic. But the main point, if I want to keep one number in my head, for the ketone aldehyde family for enolates, it's about 20. For the ester family, the carboxylic acids themselves are a little bit special because you've got an acidic proton, but after with a carboxylic acid you pull that proton off, making a carboxylate, you still can pull off a second alpha proton. And in general, as a rough rule of thumb, whether we're talking carboxylic acids or esters or nitriles, if you want to keep one number in your head, you can keep 25 in your head as a pKa of the alpha proton. In other words, a bit less acidic. These are orders of magnitude, so it's 5 orders of magnitude, right? pKa is a log scale. Every 1 unit on pKa means tenfold an equilibrium constant, so 5 is a big number, but on the scale, which might run from -10 to +50, it's still a small chunk of the scale. Anyway, 5 pKa units, less acidic, but still in the same general ballpark as esters. And again, there may be differences. Nitriles might be closer to 30, but it's not that important. If you put 2 carbonyls next to an alpha carbon, that dramatically acidifies the carbon. Because in the case of an enolate, we can only have 2 resonance structures and only 1 with a negative charge on the oxygen. But in the case of a 1,3-dicarbonyl, now you get 3 resonance structures with 2 of them having the negative charge on the oxygens. You can delocalize the negative charge. And so the pKa of a 1,3-diketone is about 9. They are substantially more acidic than a regular ketone by about 11 pKa units. For a beta keto ester, it's a little less acidic, as you might expect. It's about 11. And again, if you don't remember the difference between 9 and 11, don't worry. We're talking about 10 or thereabouts. In the case of a 1,3-dicarbonyl, we're talking about 20 or 25 in the case of a ketone or ester. All right, now let's talk about the traditional bases that we use, because I'm talking about sort of classic synthetic organic chemistry, aldol chemistry, Claisen condensation chemistry, Mannich reaction, which we'll talk about next time. All of these are sort of classic reactions. So as I said, diisopropyl amine is sort of my workhorse. The conjugate base is what we use in a reaction, LDA. That means you've got to worry about the pKa of the conjugate acid. That tells you how strong a base LDA is. pKa of diisopropylamine is about 36. And as I said, the base in mind that I keep that number associated with is LDA. Now, another go-to base in carbonyl chemistry are sodium alkoxide bases. Sodium ethoxide or sodium methoxide would be the two typical ones. If I'm working with an ethyl ester, I'll use sodium ethoxide so I don't have problems with transesterification. If I'm working with a methyl ester, I would use sodium methoxide so I don't have problems with transesterification. I'll just give you ethanol as an example. The pK of ethanol is about 16, and the base that would go along with that is sodium ethoxide. It's a very easy base to access. You just take your dry ethanol, take a weight amount of sodium, toss it in, the sodium spins around, hydrogen comes off, no fire, it's not that reactive, and you have your base nice and fresh and ready to use. Another base, another alkoxide base, slightly stronger, is potassium tert-butoxide, the conjugate base of tert-butanol. Tert-butanol, because of the tert-butyl group, isn't as good at solvating the oxyanion, and so it's a little bit more basic, the tert-butoxide, pKa of about 19, and I'm going to write KOTBU as the go-to base there. Whereas sodium reacts reasonably rapidly with ethanol, it reacts sluggishly with tert-butanol. Potassium is a lot more reactive than sodium. Sodium catches fire in water, potassium explodes in water. Sodium fizzes in ethanol, potassium might catch fire in ethanol. Sodium bubbles slowly in tert-butanol, potassium will fizz in tert-butanol. In other words, generate hydrogen and react and give you the base. All of these bases, the ethoxide, tert-butoxide, methoxide, all are related to water and hydroxide. So water has a pKa of 15.7, essentially the same as ethanol. Sodium hydroxide is another go-to base. Sodium hydroxide, obviously, if I take it with an ester, I'm going to saponify. I'm going to hydrolyze the ester to the carboxylate. So I wouldn't want to use an ethyl ester with sodium hydroxide to try to make an enolate because I would get the corresponding carboxylate salt. I should use ethoxide if I'm dealing with an ethyl ester, or methoxide if I'm dealing with a methyl ester. One more classic base is sodium and potassium hydride. Now, the pKa of hydrogen is a little bit dicey, but about 35 would be a good number for the pK of hydrogen. And as I said, the bases are sodium hydride or potassium hydride as go-to bases. I want to draw your attention to these hydrides here, because when we talked about borohydride, sodium borohydride, or lithium aluminum hydride, those react as nucleophiles. Those are reducing agents. Those add hydride nucleophiles to carbonyl compounds. When we're talking about sodium hydride or potassium hydride, they act as bases, not as nucleophiles. They pull off protons, they make enolates, but they don't, I'll say generally, but I really mean ever, act as hydride sources. All right, so I have all these numbers I've tossed out on the blackboard, which really aren't that many for these go-to bases, and I want to talk about what I do with those numbers. And again, this type of thinking all sort of runs in the background when you're thinking about reactions. In other words, students ask me, do I need to do these calculations, or do I need to know these numbers exactly and the difference between ethoxide and tert butoxide? And the answer is probably not. But where these numbers are working is in my understanding of the reaction. So for example, if I take acetone and I take sodium ethoxide, NaOET, and I look at the equilibrium for generation of the enolate, and I'll even write this as an acid-base reaction. In other words, sodium ethoxide, or ethoxide anion, a base, reacts with a ketone and acid to give an enolate, the conjugate base of the ketone, and ethanol, the conjugate acid of ethoxide. And I look at this reaction and I say, wait a second, okay, I need to know, do I have a lot of enolate or a little enolate? Okay, well, where does the equilibrium lie? Our equilibrium is going to be way to the left. It's going to be K of about 10 to the negative 4. In other words, this reflects the difference in pKa between ethanol, 16, and acetone, 20. And again, those might be approximate numbers, at least for acetone. But 16 minus 20 is equal to negative 4, right? It's a log scale, so that means 10 to the negative 4 K for our equilibrium constant. The number isn't so important, but what does it mean? It means that when you have a base that's substantially weaker than the corresponding carbon acid, your equilibrium lies way to the left. You've got a teeny tiny fraction of a percent. You've got about 0.01% of the enolate present at any moment in this dynamic equilibrium. This is sort of the complete antithesis of, say, LDA. So if I take my go-to base of LDA, and let's say just to mix things up, I'll take an ethyl ester, I'll take ethyl propanoate, and I look at this reaction, the generation of the corresponding lithium enolate, again, this is an acid-base reaction, but now the equilibrium lies way, way to the right. K is about 10 to the positive 11. Where do I get that number from? Well, I'm saying, okay, it's 36 minus 25. (10 to the 11). But the big picture here isn't that number. It is if I mix a mole of LDA and a mole of ethyl propanoate, I get a mole of my enolate. If I mix a mole of acetone and I mix a mole of sodium ethoxide, I get an equilibrium concentration of my enolate that's very, very little. And when you're thinking about enolate generation, a number that I like to keep in mind for reversible or for whether you have an appreciable amount is about 10 to the 10th for an equilibrium constant, about 10 pKa units difference. In other words, if I mix a very weak base, let's say acetate, pKa of acetic acid is about 4.76, about 5. With acetone, I really am not going to expect even any significant concentration of enolate forming. Basically, there's no enolate present. But if I mix a base like sodium ethoxide, we have some enolate. And now for go-to compounds, where if you have, say, a 1,3-dicarbonyl, like ethyl acetoacetate, and I mix it with a base like sodium ethoxide. Now that same basic principle goes ahead and tells you, okay, that's a good way to stoichiometrically generate my enolate. In other words, here, my equilibrium is going to lie substantially to the right. We have an acid with a pKa of about 11. We have a conjugate base with about a pKa of 16. In other words, my equilibrium constant is going to be about 10 to the positive 5. And again, it is not these equilibrium calculations that I am doing. It is this concept that's running in my head. LDA stoichiometrically makes the enolate of virtually every carbonyl compound it looks at. Sodium ethoxide makes an equilibrium concentration, a small concentration of enolates of most carbonyl compounds, unless you're talking about a 1,3-dicarbonyl compound, in which case it makes a stoichiometric amount. That is the take-home message, and that's what's going with the underlying having these numbers at my fingertips. All right, with all of that said, now let's start to put some of this chemistry together and say, all right, what are we doing with this? So, okay, I'll take a few examples and then we'll move on maybe to an aldol reaction. So alkylation reactions, right? I looked at addition to carbonyl compounds before. Let's look at remember, I want to put the carbonyl plus and the enolate minus together eventually, but I'm sort of starting with halves of this in terms of go-to chemistry. All right, so as I said, LDA is one of my go-to bases. If I take LDA in THF, and then I add, say, an alkyl halide, and I'll do this particular example with tert-butyl acetate. As long as the alkyl halide is good at SN2 reaction, which means, in other words, it's primary, or it's a methyl, or it's benzylic, but it's probably not heavily branched or bulky. It's certainly not tertiary. I'll get elimination there. I'm likely to get SN2 alkylation. Now, in chapter, what was it, 4? I think we talked about the Hammond postulate. Was it chapter 4? So the Hammond postulate was sort of presented as this abstract idea. The abstract idea was that if you have a very downhill reaction, you have an early transition state, if you have a thermodynamically downhill reaction. If you have a very uphill reaction, you have a late transition state. What that translates to is basically the reaction looks a lot like the reactants in a downhill reaction. This gives rise for an opportunity for regioselectivity, and I want to show you a couple of examples of this. So let us take as an example 3-methyl-2-butanone, or isopropyl methyl ketone, as it would be commonly called. And let's look at the reaction with LDA and THF. And then, as an electrophile, let's take benzyl bromide. Benzyl bromide would be another example of sort of a favorite electrophile. It's primary, and it's benzylic. And benzylic is particularly good at reaction. So what we get as the main product of this reaction is alkylation on the methyl group. And I will shorthand the, all right, I won't shorthand it for the first time, but I'm going to shorthand it every other time. I will write out the benzyl group as a benzene ring just so you can see it. So what's happening here? What's happening here is our LDA has a choice. On the one hand, you've got a sterically hindered hydrogen. On the other hand, you've got a hydrogen, 3 of them, but it doesn't really matter that it's 3, that's less sterically hindered. And as the base gets near to a proton, it's able to pluck it off. Well, the base is able to get near to these methyl groups a lot more easily. And so when we have a choice at -78 would be typical, so I'll say -78 degrees Celsius here. When we have a choice we generate, and I'll write it as OLI here. This is called the kinetic enolate. The kinetic enolate isn't necessarily more stable. In fact, by mentioning it's the kinetic enolate, it is actually less thermodynamically stable than the alternative. But the kinetic enolate ends up forming quickly. And this is cool because it gives us this element of regiochemical control, whereby if I have a choice of pulling off 2 protons and I generate the kinetic enolate, I can select for the less sterically hindered position. Now, organic chemists are never happy to just have one choice. You always want to be able to have control in organic synthesis. And so a lot of efforts in synthetic organic chemistry say, if nature wants to give you one thing under one set of conditions, can we develop conditions that give rise to a different product? Can we get either? Can we have a choice? So, of course, what I'm talking about here as the alternative is the more substituted enolate. And it happens that this enolate is more thermodynamically stable because more substituted double bonds are generally more thermodynamically stable. You have more electron density from the alkyl substituents being donated into the vacant pi star orbital, stabilizing it. In general, less substituted alkenes, more reactive, more substituted alkenes, more thermodynamically stable. So this is what is called the thermodynamic enolate. And as you might expect, if we can generate the enolate under equilibrating conditions, then we can generate the thermodynamic enolate and go ahead and get its product and control the regiochemistry of the reaction in the other fashion. So under the previous example, usually you would use 1.5 equivalents of LDA. I haven't been that fussy as to specify it, but typically the way I would run this reaction is to take maybe 1.1 equivalents of diisopropylamine, or maybe 1.2, put it into THF, chill it down to 0 degrees, by syringe, add usually 1.05 equivalents of N-butyllithium, which I've titrated to make my LDA. Let that sit for 15 minutes, chill it down to -78 with a dry ice bath, drip in my ketone to generate the enolate, let it stir for 15 or 30 minutes to generate the enolate, add my electrophile, and allow the reaction mixture to warm gradually. But if I do the antithesis of this, if I go ahead and use 0.95 equivalents of LDA, for example, so there's always some ketone around, then the ketone can go ahead and exchange a proton with an enolate. You may get the kinetic enolate first, but your reaction mixture can equilibrate, particularly if you allow this to occur, let's say, I'll say and equilibrate, meaning longer times or higher temperatures like 0 degrees, or we use a base like potassium hydride in THF at, say, 20 degrees Celsius. That gives rise to mostly, and I guess I'll continue to write it as OM as the main enolate formed. And so I could expect, if I carried out this generation of the enolate, generating the thermodynamic enolate, and then added my benzyl bromide, I would get as the main product the benzyl alkylation on the more substituted position. All right, so that kind of gets us into the swing of carbonyl electrophiles and enolate nucleophiles. And it sets us up to talk about the Aldol reaction. And to make a point, even though I'm writing a title here, I'm writing Aldol in lowercase. Aldol is not the name of any person, unlike, say, the Michael reaction or the Wittig reaction or the Diels-Alder reaction or the Claisen rearrangement or the Cope rearrangement, all of which are named after people. Aldol reflects that you have a carbonyl and an alcohol in the product, and indeed the parent aldol from acetaldehyde is called aldol because its composition, while not completely known initially, was given that name because it had an aldehyde and an aldol and an alcohol group. All right, so I will just take some ketone. I'll take tert-butyl ethyl ketone. That's a carbonyl, really ugly here. All right, and again, I will, for starters, take my favorite base, LDA, in THF, and then I will go ahead and I will, to put the pieces together, add an aldehyde. I'm choosing benzaldehyde as an example here, right? This is just a shorthand for a benzene ring and an aldehyde group. And finally, we carry out some sort of aqueous workup with aqueous acid. I usually will use aqueous ammonium chloride, which is a very mild workup. And all of what's going on in my head, and indeed all of what's going on in the flask, is we generate the enolate. The enolate attacks the carbonyl. We get the corresponding alkoxide. The corresponding alkoxide protonates on the third step on workup, and we end up with the aldol product. What I like about this set of conditions here is this really is a good workhorse reaction. It's sometimes called the directed aldol. Oh, thank you, Sebastian. It's a good workhorse reaction. It is the sort of reaction you can do with almost any carbonyl compound. Aldehydes are a little funny. Aldehyde enolates as nucleophiles are a little hard to generate. You generally can't take an aldehyde with LDA and make the enolate. They tend to self-condense and give a mess. But for almost any other compound, a ketone, ester, nitrile, even for making the dianion of a carboxylic acid, this works. I know I mentioned earlier my beloved lab in the Chem 160 course, which is the first lab in the class. It's an Aldol reaction to teach recrystallization and butyllithium and syringe techniques. And we do that lab with LDA and THF in the first step, benzophenone as the ketone, aqueous workup. Again, I'll write H3O plus. We use my favorite workup, aqueous ammonium chloride, in the lab course. And we get, in this case, this nice crystalline compound. And really what makes this chemistry beautiful, but what makes organic chemistry beautiful in general, is that organic chemistry, although we can carry out a million different reactions from what we've learned in sophomore organic chemistry, in other words, we can combine on, say, a sophomore organic chemistry exam, one of any dozens of ketones or esters to make the enolate, with any dozens of ketones or aldehydes to act as an electrophile, and we can predictably make the product. All right, I want to go in a little bit more into mechanism and conditions and come back to curved arrows, and I want to go back to the very first sort of Aldol reaction, the eponymous one for which the Aldol reaction is named. If we take acetaldehyde and sodium hydroxide and cook them up, or let them sit rather, at 4 or 5 degrees Celsius, basically in a refrigerator or an ice bath, we get, albeit a not fantastic yield, the self-condensation product. And what I want us to do is to be able to write curved arrows. You should all be able to write curved arrows for this mechanism. I'll be good at first and then less good later on, with some deliberateness in writing my curved arrow mechanisms. And so we can think of this as equilibrium formation of the enolate, hydroxide pulls a proton off, we generate the corresponding enolate, also a mole of water. The corresponding enolate, all this chemistry is reversible, by the way. The corresponding enolate kicks down, and again, I love to write this resonance structure of the enolate and just realize that it means that we can think about the negative charge being on the alpha carbon without necessarily writing it there. And so the enolate adds to the corresponding carbonyl. To give the aldolate. And the aldolate pulls off a proton from water to give the aldol product, which we can fish out. And if you look carefully at this reaction as I've written it, you'll notice that hydroxide is acting as a catalyst. We are consuming the hydroxide in the first step and regenerating it in the last step. In other words, hydroxide is catalyzing the reaction, making it occur without actually being consumed in the reaction. All right. Conditions matter, particularly in these type of cook-em-up reactions with hydroxide or ethoxide. And so if I take basically the same conditions, I'll take butyraldehyde as an example. I'll take sodium hydroxide in water at reflux. I'll even be a good person and write the water below the arrow. And I write it. Then we can expect to get, and indeed do get, the alpha-beta unsaturated carbonyl compound in what's sometimes referred to as an aldol condensation. Condensation means loss of a molecule, usually loss of water. So it's the aldol reaction with dehydration. And by way of refresher, under these types of conditions, with heat, after we get the aldol reaction, just like we did on the previous board, we can continue to generate enolate. And now that enolate can undergo elimination to kick out hydroxide. And take us to the alpha-beta unsaturated carbonyl compound. And again, all of this is stuff that you've seen in sophomore organic chemistry and should only be by way of review. And plus, this is a good excuse for us to write mechanisms. And the last thing I want to do in talking about the aldol reaction is simply to remind us of what's sometimes called the crossed aldol. The crossed aldol reaction is typically of an enolizable ketone with a non-enolizable aldehyde. And often this reaction can occur with control because aldehydes are more electrophilic than ketones. So only the ketone can generate the enolate, but the aldehyde wants to react more. And so if I take, say, pinacolone, as it's called, 3,3-dimethylbutanone, and I mix it with benzaldehyde, and cook that up with, say, sodium hydroxide in, let's say, water with some ethanol. You'd add ethanol as a co-solvent, and I let them react at 25 degrees Celsius. You get aldol with dehydration, but only one component, the ketone, can generate the enolate, and one component, the aldehyde, is more electrophilic, and so the overall result is that I get, with some sense of control, I get a single product out. All right, well that takes us to the end of today's lecture, and where I'll pick up next time, I think, on Monday, is talking about the Claisen condensation, and then maybe on to Semantic reactions or other nitrogen chemistry. All right, I will see you on Friday. Good luck with the midterm exam. It will be straight from the book.